All right, we're on. Hmm. Oh, you know what? You're actually not coming through. Yeah, of course, that happened right as we start. So, hmm. What is what is the problem with that? Because I can hear you just fine. Well, why don't I try again? Try again? Nothing. Hmm. Okay, so I guess we should just start. You know what? I'll give myself one more minute to troubleshoot this, and then we'll start. Let's try our best to get this fixed. Now, let us. Okay, why? Doubly insane? Is that where you're? Hmm. Let's see properties. Oh, wait a second. Maybe. Wait. Oh, I'm glad that the first thing that came through was you just randomly singing to yourself.
Well, I wanted to give you some testy tests for your audio beats.
Okay. I think I'm gonna turn myself down just a little bit, and then I think you should say some test words.
Wankel rotary engine.
All right, very good. All right. Okay.
Okay. So I was saying the stream feels more comfy today. Did you get this reupholstered?
Yeah, velour is in fashion.
Oh, okay, yeah. I mean, I wasn't complaining about all the velvet before, but the velour is kind of, I don't know, it's an interesting texture that we have for the stream. Yeah.
Yep. So,
it's cozy. It's like a mountain hideaway, but a stream.
yeah, it's like one of those. It's like a cave hideaway.
Yeah.
That's been,
but it's
like completely done up as a game room.
Yeah. Despite what people say, it's not dank though. It's not a dank cave.
No, of course not. No, it's a.
That would make it more of a grotto, you know.
I couldn't say.
Yeah.
Is a grotto a cave?
No, it's not.
Okay, you had got me. I was like, wait, no, you're right. A grotto is a small picturesque cave, especially an artificial one in a park or garden.
Yeah. Yeah. Usually there's water in a grotto though, right?
I couldn't say. As I said, I didn't really even know what a grotto was.
I think I'm gonna image search grotto, see what we get. Yeah, usually grottos it's like a watery cave. A little watery cave, a little tucked away. This is what we're learning today.
So I'm very pleased that the lecture got off to this start. It's the most productive lecture that I think we've had so far.
Yeah, people are expanding their horizons.
Yeah, I thought a grotto was like a. I honestly, if you'd asked me, I would have thought it was like a little, basically like oasis inside of like a forest with maybe, water or something like that. You know what I mean? Like a little opening in the, But I guess it's some kind of, I don't understand. Anyway, okay.
Yeah.
So you want to talk about algorithmic analysis again?
Oh yeah, let's do that. So let's talk about. So we talked about algorithmic analysis. We defined the O's, the thetas, and the betas and the omegas.
Yeah.
And
So
all those other
why
things.
don't we? Because everybody always gets it the first time, Ben. There's no reason to review it, right?
Especially these guys. I mean, holy cow. The cerebellum's going to work on these, like in the chat with these students. They got it already, but they're we're gonna re-explain it just to to really cement their already uh Herculean understanding. That doesn't even make sense, but I'm okay. I'm just ensconced in velvet. Groaning 1 over
All
groaning.
right, let me just say some words. So, what is big O?
It's not a small O.
No, there is little o, but we ain't talking about that.
It, little o is like when you guarantee it's the tightest bound, right?
Oh God, now you're putting me. I think little o is. It's a weird opposite of. Crap.
Don't worry about it. Don't worry about it. Don't worry about it. Don't worry about it. Let's keep going.
Wait.
I'll look, and then you keep.
Oh no, I've already looked.
Oh.
So if. Oh God, I found the worst possible definition of it.
Is it this NIST one? NIST one's terrible.
Yeah, I always forget with little o. I'm always very cautious about saying anything about it. Oh, I see. So little o is a strict upper bound, and then I guess little omega would be a strict lower bound, because it says if f for every. Oh no. Oh yeah, okay, yeah. So it's like a strict asymptotic upper bound, because it says for every positive constant, f of x has to be less than or equal to epsilon times g of x. So that basically means that you can like shrink down that constant epsilon as much as you want. And yeah, anyway, but we don't care about little o. So what is big O? Big O means that we would say f is big O of g when f of n is less than or equal to a constant times g of n. And then, of course, we get to apply our silly word eventually. Which you know, anyone who's a math person or, feels more comfortable hearing it this way. So this is definitely fine if you feel more comfortable just thinking about it like this. What we really mean is as n goes to infinity. And so what we're talking about is the limit as n goes to infinity, right? And technically what we could even do is look at it as like a ratio of, f of n over g of n. And so as long as the limit of f of n over g of n goes to some number, then that's what we mean by eventually. And I probably won't say any more about eventually. Other than that, okay, so what does it mean to say that something's an upper bound? What it means is that if you have some function, well, that's terrible. Let's actually just do it on that like Demos site or whatever it is. What is it called? Desmos. Here we are. Let's do y is equal to like x cubed minus 2x squared plus 1, right? So here's a cubic function. It's my favorite cubic function. And now let's look at, say, y is equal to, say,
favorite cubic function.
Nah, well, you see, that's the mistake you made. You do not have a polynomial expression. So, and then of course we have to fix the again? Domain. That's what mathematicians call it. We call it the
Mm-hmm.
So we see here that this blue function, right, eventually, meaning around here, like at around 0.5 here, crosses 5x cubed minus 2x squared plus 1, and it stays that way forever. So what we will say is that in this case, we would just say something like, 5x cubed minus 2x squared plus 1 is, and I usually use this word is for various reasons, big O of x cubed. And the reason is because when you pick the constant c is equal to 8, what you're going to get is that this, 5x cubed cubed plus junk terms is less than or equal to 8x cubed, eventually. Okay, cool.
So what does this mean? What does this mean for programming?
Well, so yeah, I mean, so you always like to rush right into that. I think it's important to do the mathematical understanding as well. But the thing here is that, yeah, so for programming, what it generally means is that, how should we say it? We should say it in a way that, like, an algorithm that takes, say, f of n steps for input of size n will be similar similar, I guess, or less than in time, right? So it'll go, so we could say similar or faster than basically just some number, just then like some constant times g of n seconds or steps, right? So that's kind of the way to describe it. Is like an algorithm that takes f of n steps for an input of size n will be similar or less than some constant times some just simple function g of n, right? Mm-hmm. All right. I think that's the way we really think about it, and so that's like the way we think about it. So what we think is, I think this is kind of probably more along the lines of what Ben's looking for, is something along the lines of, like, we think that usually we'll say that algorithm f is at least as fast as algorithm g, or that's, and of course, like, the problem with that is that there's that constant floating around, but this is what we usually think about, is if we say something takes like O of n squared steps, we think like, oh, okay, so as we increase the input size, it should take, if you have an input size of size 10 and it takes 10 seconds to do, and if you make that an input size of 100, then you'd be like, okay, so this is multiplying by a factor of 10, but if we have something that's O of n squared, then we expect it to take 10 seconds times 10 squared, right? So we would expect it to take 1,000 seconds. Okay. So let's quickly review big omega and big theta. So here's big omega, and don't ask me about stupid little omega, though I think if we're following our intuition, then it would have to be the same thing as little omega, right? It would have to be like some kind of strict epsilon defined lower bound or something. I think that's why we don't even teach it in 3. Do you teach it in 341?
What about an omega that we don't? No, we don't teach it. What about an omega that we don't make any like judgment calls about its size? We just say, just write omega. Is that a thing?
I don't know. I don't know.
Yeah.
You mean
Anyway.
do you mean in terms of Greek, or do you mean in terms of computer science, or do you mean in terms of, what do you mean?
I just mean, like, there's big and there's little. Why can't we just have like a norm, just have omega? Be like, hey.
Oh, well, I mean, normally if you ask me like to draw them, well, actually that's a good question. I don't know what I would do. Anyway, so
all right, let's get onward.
F is crap. Cool, that's nice. Omega of g when, and the same mathematical definition applies. It just says that f is now bigger than or equal to c times g eventually. And I guess we can put little of n's if you guys want. Sometimes people feel deprived if you don't know what variable the function's eating. So, yeah, so as I say, all of these words have the same meaning, except now omega is a lower bound. And so one way I was telling students to think about it, and so if you want to think about it in terms of programming, is you say an algorithm that takes time g, right? Algorithm g is faster than algorithm f, right? And with all the caveats. Caveat 1 is eventually, and caveat 2 is on large enough inputs, right? So technically both of these are required, but yeah. Okay, and then so the way I was telling students last semester, I don't know if this helped or not, is that omega, it has this bar on the bottom, right? These nice little things, and so that means it's a lower bound. And O is like overestimate. And that's what big O means. It could be a tight estimate, but it could also be an overestimate. And then, so what is theta? So theta is so if f is theta of g, that means that there's a constant a times g of n, which is less than or equal to f of n is less than or equal to a constant b times g of n. There we go. And of course the same caveats apply eventually, and then after, or on large inputs. And so the other way to say it, before we get into the programming meaning of it, is that if something is theta, then that means it's both, right, big O and big omega, right? Because it's both an overestimate and an underestimate, so we would call that like a tight bound. And okay, and then finally, how do we think about it? What we'll think is that basically f runs very similarly.
No better, no worse.
And of course, we have to kind of ignore these constants when we say runs very similarly. It could be that these constants are like 100 or something. So it could be that f runs a factor or two faster than g, but the more accurate way to say it runs similarly is that the runtimes change proportionally. I think that's almost the better way of saying it. It's like as the runtime of f increases, the runtime of g increases in the same way, right? But that, I mean, yeah. Okay. Have I been enough of a lawyer here? Can we go back to programming now?
Yeah, let's go back to programming.
Okay. Yeah, I mean, the problem...
We get it, you math!
Well, I mean, the problem, right, is that there's just so much, like, technical detail here that I'm trying to force myself not to say. Does that make sense?
Yes.
And it's difficult because you want to say it.
I'll ask the question you always get. What do we need to know for the exam?
Oh, that's a good question.
Is it? I don't know.
Well, I mean, it's an annoying question, but it's unfortunately not a terrible question.
It's not always an annoying question. Sometimes it's reasonable.
Well, I mean, do you want to discuss what we should expect for them to know for the exam this time, or what should we do?
I don't even know. What should they know for the exam?
I mean, I think, I guess you should know, like, So we used to have people memorize all the sorts and searches, right?
Yeah.
But that went terribly.
Well, the problem is that when you get to higher level classes, you're expected to be given any bit of code and then say what function it is big O of, which we don't expect you to be able to do now because that's something that, you do in 341. But we do want you to have some familiarity with it now so that when you get to 341, you're not like completely brain exploded because it's like, what is all this stuff?
Yeah, I
So,
mean,
but telling everybody to memorize what bubble sort is, that bubble sort's big O of n squared, makes it seem like it's just, oh, you just memorize it, but it's actually something you can derive. But we don't want to go through all of the how do we derive it
we
because that's
don't.
hard. I mean, I don't. We want to go over it in class, but I don't know if we would expect a level of mastery from them on the exam to be able to do that. I don't know. What do you?
I don't know. Why don't we just do the lecture and then we'll come back to this question?
Yeah, we'll come back to that.
Because this question is a complicated question.
It is a difficult question. The next exam is the final, correct?
So I'm just gonna go through. I think we'll start at bubble sort. We'll do selection sort. Or have we done in selection sort, or do we do?
Let's just start it from the top.
Well, the top was swap, which we already did.
Okay. And what was swap, chat? Pop it in the chat. What is it big O of?
What is the runtime? Swap.
What is the runtime? Is big O of what? Big O of question mark. What is it? What is it, guys? 42. Actually, not wrong, kind of. Do finals have to be in the 2-hour window established by the registrar? No, they do not. If we can issue any kind of final we want. They will probably overlap that. But yeah. We'll probably be doing it. We're doing a take-home final again, right, Eric?
I mean, you guys are home, right?
Yes. So, yeah, constant time, right? Because
constant
no
time.
matter how big the list is, you're just going to swap two things. So
now, normally we'll say O of 1. Like, we usually say O of 1. You can also technically say omega of 1, but that's pointless because all that's saying is that it's no worse than a constant, which means that it takes no worse than one step. Which, okay, that doesn't tell us anything. We can also say theta of 1. So normally you would just say O of 1 because that bounds it from above and says it's no... it's no better than a constant is what I mean. And so since it's no better than a constant, but it cannot be any better than a constant, right? So, anyway, so then basically we talked about our little primitive bubble sort here, right? And primitive bubble sort, yeah, I mean technically there's a constant that's better than a O of 1, which is O of 0, which is the algorithm just, I guess, does nothing. Like doesn't have a body of the function, it's a pass or something. But even that's O of 1, so I don't think you can have an O of 0. So if you guys remember what we did with the primitive bubble sort,
if there's 10 things in the list, how many times do we run that if statement? I guess.
Yeah, so if we do it kind of more kind of sledgehammery and we don't worry about this -1 and we don't really worry about this if statement and the swap, we just say all of this is constant time, so this is O of 1.
Yeah, the if statement's O of 1. It's either one operation or two operations.
Right, and then we say this for loop is going to run the length of the list times, which is n.
Yep.
And
how many times are we going to run that for loop?
And then the outer loop is going to run n times. And so the thing is that what is that really saying to us? That's saying to us that, let me just erase this. It's saying that, and I think I've written all this down before, but I don't care. So the outer loop runs n times. Then the inner loop runs n times. And then for each time that the inner loop runs, we do all that code in the middle. So you can say 4, or you can say 1, or you can say whatever, right? This is just the number of steps. And there's like an if statement plus the 3 steps in the swap. So I'm saying 4. Again, that's the whole point of big O, is that this 4 will end up not mattering. That'll be the same thing as 1 since it's a constant. So here we're going to get 4n squared, and so then what you'll say is that 4n squared is O of n squared, right?
Yeah. And so what this all boils down to essentially is we're looking for parts of the code that run a certain amount of times in proportion to the size of an input. And so usually just normal sequential program control where it's just one line after the other doesn't run proportional to, it's just one line after the other, right? It's just like if there's 3 lines, it runs 3 lines. And if it's conditional, like an if statement, it either runs the line or doesn't. That's not really, I mean, it's not really proportionate. But loops, on the other hand, can run in some proportion to the size of the input. So you have to look at the loops and ask yourself, is this running once for every element of the input? Is it running once for n, like the size of the input squared, and so on and so forth? So when you're doing this kind of analysis, you're really going to be way more sensitive to looping structures. And someone inevitably in chat will ask, well, does that count recursion? Absolutely, it counts recursion, and we will get to that momentarily.
Yeah, let's not jump ahead.
We're mostly, when we're doing this kind of analysis, our eyes should be caught by fors and whiles, because those are the things that care about the size
for
of the
loops,
input.
while loops, and function calls. Because a function call, whatever that function calls, you have to compute the big O of that. And if it's a recursive call, then it's a separate thing. But even if it's just a function, right? The whole point here is that when I was looking at this thing, I was saying, oh, swap here is O of 1. But if swap here was O of n, then instead of being n squared, this would be n cubed, right? Because for every time we go through again, and then we do an O order n operation, and then we would have to multiply n times n times n, which would be n cubed. So, like, we do actually have to look at... at first, when I remember learning Big O, I remember there being a textbook that kind of buried a lot of the details like that, and didn't actually mention that you had to compute the stuff about function calls, and they were like, oh, well, this algorithm might run an O of 1 time or O of n time, but we're going to compute the big O of this other function. And I was like, well, you can't do that, right? Because otherwise we could just stick this for loop into a function and it wouldn't matter, right?
Yeah.
So, there should not be a way to rearrange the code by sticking it secretly into another function that changes the actual runtime of the function, right? So, anyway, okay. Let's look at this.
We get n squared for this one.
Yeah, we get O of n squared, we get omega of n squared, we get theta of n squared. Now, why do we get all 3? We get all 3 because it can do no worse than n squared, it can do no better than n squared, so that's omega, and therefore it has to do exactly n squared. And the reason why is this primitive bubble sort doesn't actually take into account the thing that the bubble sort down here does, right? So the bubble sort down here, let's look at this one. So what does this one do? It has a while swapped, so while swapped is equal to true, and while I is length less than the length of the list. So remember what this bubble sort is doing. So if you use built-in functions in Python, yeah, technically, but of course, yeah, technically.
You do.
Yeah.
I mean, you any functions you call, you have to be mindful of.
I mean, the answer is yes, but a lot. So I guess it depends, right? Like the min function is built in, but and that's O of n. Like the sum function's built in and it's O of n. But like the print function, you can generally assume that's O of 1. Generally.
Yeah, generally. Basically, the thing you're going to care about is if you're doing a sort, the size of your input is the size of the list. So you should really be mindful of any function that
is dependent on that.
If you send that list to a function, then you're going to be worried. If you're sending some random like variable that's just an integer to some other function, like that's just one integer. What could it doesn't even know about the list. It can't be slower than constant time. So you want to be really mindful of any functions or operators that you use on like lists when you're doing. Now you can do asymptotic analysis for things that aren't list operations, but we're not going to do that in this class. So yeah, basically, if you're doing some operation to a list, you should have some sense of how fast it is. Like the if I wrote if one in list, that little operation, that's linear time because it's actually going to do a sequential search.
Yeah, because I mean, what that's secretly doing is a little for loop through the list, right?
Yeah.
Yeah.
And in fact, a lot of the times that you're going to be using asymptotic analysis professionally, and I mean, I actually was just talking to a friend on a fun project we're doing on the side. We were talking about Big O performance, actually, of database operations. And that's usually what you're going to be looking at, all of the functions available for you to use from like a library or something like that. And you'll be thinking about, well, how well do they perform for what I want to do, and so on and so forth. So that's actually when built-in functions and library functions are actually when you tend to use this in more practical settings.
Yeah, the real concern is whenever you're dealing with something of size, like starting at maybe 1,000, but really when you get up to anything of size a million, is when linear will still perform okay, n log n, which we're going to get to, will still perform okay. But if you have something that's like an n squared algorithm,
You're done.
and you're doing it on something of size 100,000 to a million or something, and you're like, oh, this is a website. It's like, nope, you might as well mail it. So
yeah.
Okay.
Anyway.
All right, let's get back to bubble sort. So this version of bubble sort is a little different, right? This version of bubble sort is what it does is it does basically the same thing, except it keeps track of when it's swapped and when it hasn't swapped. So if it goes through the whole list and it never swaps, right? Swapped is equal to false here. It can go through the list in this inner loop. If it never swaps, right, then what happens? Then it doesn't set swap to true, and so then it says while swapped. So the point is that it'll break out of this loop, and once it does that, then it'll terminate. So in the worst case scenario, bubble sort has to go through all the times, which means that I has to go from 0 up to the length of the list. So this outer loop in worst case scenario is gonna go through n times. This inner loop, right, always goes through. Actually, it doesn't.
Well, one question to ask ourselves. Let's ask chat. So we had primitive bubble sort that doesn't do the swapped tracking. We got this bubble sort. Which one's faster, potentially? Which one's potentially faster? Anybody? Class, Bueller? Which one's faster? But primitive or this primitive paleo or neo? Bubble
Well,
sort.
I guess the way to say it is like, primitive has less code, so it's better, right?
Ow! I wish I could give you a hug over the internet right now. Yeah, right? There's less code, it must be faster.
Yeah.
But it's not, actually. The new bubble sort could be faster in certain cases, right? So, because if you give a sorted list to our new bubble sort, it'll loop through it once and be like, hey, this is sorted, and then stop. So that's faster. So then what changes, the big O or the big omega? If it's in that case.
I guess we should really say first what changes, the best case or the worst case. Like,
is the best case better or the worst case better? Silence descends on chat.
Yeah, I think people are like, I hope someone else answers. So everybody answer in 3, 2, 1. Type something.
Okay, yes, thank you, Max. So the best case change, because the best case is the best case is that you get a sorted list, which means that you only loop through the list once. So if I'm only looping through the list once, what is my big omega in that case? Like, what function would I use to characterize going through the list once?
Well, let's see what happens if we only go through the list once, right? That's
Yeah.
the real question.
Yeah.
So if you only go through the list once, right, that means that I is equal to 0, swapped is equal to true when you come into the loop. It sets to false. Then it goes into this inner loop, right? For range len the list minus I, which is 0, minus 1. So it's going to basically go n times, right? We can't stop it because it's a for loop and there's no breaks or any craziness. So you go through the loop n times, and then finally, right, you pop out, you add 1, and then you return up here to the while statement, but swapped is equal to false because we never entered the if statement, right? So, how many operations did we just do? Right, we did n operations where we increment j and we check the list. It's, we don't enter it. So, yeah, I see people saying it, so I agree.
So it's if in the best case it's already sorted, so the inner loop runs once and it's linear. So we get our best case is big omega of n, because omega characterizes I can do no worse than this.
Yeah,
So that's my best case.
So last semester I said some really confusing things, and so this semester what I'm going to say is that the best case of the entire algorithm is an n runtime, which is why the algorithm runs in omega of n. Right?
Yep.
Okay. I think that's the best way to say it. Yeah, anyway, okay, now that I've said that, let's so what is the worst case?
Yeah, what's the worst case?
So in the worst case, what happens? Well, the same thing that happens in the primitive bubble sort, right? It just keeps looping around and it won't stop because you're just going to have to keep incrementing this, and at least once, right? The real bad scenario is like it swaps one time, let's say, or a few times, right? If it basically swaps once, then it sets it to true, so we have to go through the next time. So we only needed to do that. We only needed to swap one thing per cycle here. This loop is a little bit wonky because it's actually the length of the list minus I minus 1. So you're going to love this one, Ben.
Will I?
Yeah, I think you will, right? Because, so we have to make an argument that, so what we want to say is we want to say it's O of n squared. Right? That's what we want.
We want that.
But what we really have is this. We have the sum from I is equal to 0 to n of n minus I minus 1. Right?
Yep.
And so, what does this mean? What this means is that if we get rid of the minus 1 because I don't care about it, what we really have is just n minus I. I mean, if you want, you can always just... So one thing we can do is we can distribute the sum over all these things. So we can say it's the sum from I is equal to 0 to n of n.
No. I believe that we don't care. You don't have to algebra me.
Well, I'm going to do this anyway because we need to do this for the next step. Minus the sum of 1, I equals 0 to n. And so this one, summing up, whatever, who cares? This thing is actually going to be n plus 1 because we're adding it up from 0 to n times, right? So adding up n plus 1 times will give us n plus 1. Adding up n plus 1 times is going to give us n times n plus 1. But then what the heck is this thing going to give us? This is the only thing that I actually care about. The sum of I equals 0 to n. Well, as it turns out, there's a rule for this, that it's n times n plus 1 divided by 2.
Yep.
And so this is the Gauss sum.
Ooh, Gaussy.
Yep. And so, because that's one of my favorite sums, and because I saw that little bit of code there, we had to talk about it. But the good news about the Gauss sum is that even though it's adding up like 1 plus 2 plus 3 plus 4 all the way up to n, it's actually it's still just O of n squared, right? So we look at this first term. This first term is n squared plus n, so that is O of n squared. This second term here is n times n plus 1 over 2, so it's essentially the same thing as this, except it's divided by 2. So technically, you can either subtract or whatever you do, so it's O of n squared. Oh, we can't actually do it this way because we don't know the constants, so we actually do have to subtract. Because this is 1/2 of n times n plus 1. The good news is that a whole of an apple minus a half of an apple is a half of an apple. And so, did you like that one, Ben?
Yeah.
Anyway, that's the good news, is that we get a half. A half doesn't matter because we're dealing with constants, so then we get to just say that this is all O of n squared.
Yeah.
So and we're done.
So people are getting overwhelmed, and that's natural because this is the level of analysis we expect you to do in 341 after you've taken 203. So Eric will get his 203 clause on into you at some point, probably, and you'll be learning how to do all this stuff. But for now, the idea is that we have characterized that even our optimized bubble sort is still big
O of n squared.
In its worst case. So best case is omega. Oh, omega so good, omega. Best case. And then big O is like big O. Oh. But that's worst case. So big O characterizes, well, what happens on your worst day, right? So like when you accidentally take a selfie with your phone, and it's like you look like Jabba the Hutt because you're like looking down at your phone and you accidentally take a selfie. That's your big O. That's you as a person in the big O function. Like you don't get much worse than that. But then like whatever you guys post to your Instagram social medias, that's your big omega. That's the best face you're putting onto the world. So if somebody walked up to Bubble Sort and they said, "Hey, how fast are you?" Bubble Sort would be like, "Oh, some say that I'm linear." And I'd be like, "Yeah, but yeah, that's your big omega analysis. Let me see your accidental selfies," and be like, "All right, I'm n squared. Damn." So that's why we have these two different kinds of analysis, because some algorithms will perform well under certain conditions, so we want to give them credit for where they do well, but we also want to keep them honest and say, yeah, but you can be really slow sometimes.
So yeah, okay, good. That's all nice and happy. So the bubble sort is O of n squared, omega of n, and what is it theta of?
Nothing.
Ah, right. And it's theta of nothing because if the omega and the O don't agree, right, then there cannot be a theta, right? So a theta is a type bound. And so if there's no, if the best case doesn't agree with the worst case, then yeah. Well, we're about to do the thingy anyway. So okay, let's blast through selection sort because we did talk about selection sort. So selection sort is theta of n squared. And the reason why it's theta of n squared is what? Mainly because we see we have a loop and we have another loop. Both of them are... Actually, this one is the same Gauss sum business as the previous thing, but we know we don't have to care about that, right? Like, that's the whole point of that argument, is that we don't have to care. So we have a loop that goes up to n. We have a loop that goes up to essentially n minus I minus 1, unfortunately. And then, so we know that the sum of that is just O of n squared. Can it do any better, right? What is its best case, right? Well, unfortunately, its best case is the same as its worst case, right? Because every single time it scans through the list, and it scans through the whole list starting from I plus 1 to the end. So it's never going to do better than than the most number of times it could run. Because, well, I guess I should say that it runs exactly the same number of times, regardless of the like overall shape of the list. So if the list is really unsorted, or really sorted, or just completely sorted, or half sorted, half unsorted, it doesn't matter. Selection sort will do the exact same number of steps. Okay, so let's turn to. Should we talk about binary search?
Yes.
Next.
Yes. Because I have a thing I want to harp on about binary search. Because
Okay.
that'll get it in their brain goops when they hit 341, and I try to put it back in there.
All right, so I don't even know if I have binary search written up here. So let's write up binary search. Oh yeah, because I think you did the lecture on it. So whatever. Binary search, and we have like the list, and we'll have like start index and end index, right? And we'll have like middle equals start plus end minus start divided by 2. And then what do? We say if middle, or if the list at middle, and I guess I should deal with a base case. I might do that in just a second. Oh wait, and the element we're searching for is equal to the searched element. We can return true. Elif the list at the middle element is equal to, or is, we have to be careful now, is bigger than the searched element, right? Then we want to return binary search on the list start middle search, right? We want to go up to the middle, because if the list at that element is bigger than the thing we're searching for, we want to go to the first half of the list to search it, right? Cool. And then similarly for the list middle is less than search, we want to return binary search. And what do we change? We go from the middle to the end. I guess we can go middle plus 1 maybe, or something like that. I don't know. And else. Oh, I see. Okay. And then let's put our base case up first. So if not the list, right?
No, it's if start equals end. You're not making the list end.
Oh yeah.
Oh yeah, or not the list. Yeah, I guess. I guess if somebody asks, is this thing in this empty list? You'd be like, nah, buddy.
Well, okay, let's ignore that for now and just say if start equals end, and the list at, say, start, because that'll also, so if start is equal to end, then start, middle, and end are all the same, right? There we go. So, okay, so this is kind of, I don't even know, we should probably test it out, but we're not going to. Because there's a small potential that it will break, and then but this is essentially binary search.
Yeah, if you want to see the lecture on getting it to work and walking through how it works, that's already out there. But we're just going to talk about the analysis of it.
Right. So it's always possible that this exact version might have a small bug in it that, for like weird middle cases where there's like 2 elements, or I don't know what. I haven't tested it. So as I just rando typed it in. So okay. All right. The one advantage of this algorithm from the previous one is that it doesn't make copies of the lists, right? So it's not using slices every time, which would actually decrease the runtime. So that's why I wanted to type this one in, because it's actually the binary search that will get the correct runtime for binary search.
Correct.
So what happens? Well, I guess we look at an example, right?
Yeah. And also, there's no loops here. So that's already like...
Yeah. What's a loop?
What's a loop?
What's a loop? So basically, let's go through and just look at the worst case scenario about what happens here. So the worst case scenario, let's say that we have an element 7, and then we have 15 and 22, and let's make the list a little bit bigger, because otherwise this will be very short. 1, 3, 4, 5, 6.
Or is there like a visualization we want to look at?
Well, I mean, we're kind of looking at the visualization. I guess we can do that too.
It just saved you a lot of writing.
Yeah, well, I've already gone through a huge amount of the writing, so we'll just do it this way.
Okay.
And then let's add to 32, 37, 91, and 100,000. No, okay, I'm kidding, 102. So if this is our list, and what should we search for, Ben? Let's search for 92.
42. Okay.
Let's search for 92. 42 is good too. So, if we're searching for it, then we count up the number of elements in the list. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12 elements in the list. Divide that by 2 to get the middle element, because the start's going to be 0 here, and the end is going to be God knows what. And I guess the end is going to be 12 or 11? 12. 11. 11. The last index. So, okay. So we get 12 divided by 2, which is 6. So we'll do 1, 2, or 0, 1, 2, 3, 4, 5, 6, right? And so is 42 on this side or this side? And the answer is here's 15. So it's going to have to be on this side, right?
Yep.
And so it depends on how your implementation works, whether you take 15 or not. So let's take 15. Not that it matters, like you can ignore 15 or you can take 15, but it's going to do the same thing either way. Okay, so now we have a list of size 6. So now we're going to look at element 3, right? Because 6 divided by 2 is equal to 3. And so what about this element? So we know that 42 is bigger than 37. So now we're going to look at a list of size 3. 37, 91, 102. And then, so 91 is bigger than 42, so we're going to look at this one. And finally, we get down to a list of size 1, right? So here we had a list of size 12, size 6, size 3, size 1, because we're dividing the list in half each time, right?
Yep.
Okay. So, what kind of runtime do we get when we divide something in half every time? So the answer is, well, so in this case, it's like 4 steps, right? So when n is equal to 12, the output is 4, right? And so, as it turns out, what we're really asking is the number of times you can divide it. So we're asking the number of times you can divide by 2. So we're saying, like, take n, divide by 2, then divide by 2 again, 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 etc., until this is equal to 1, right? Well, if we clear denominators, right, so we push this 2 up here, we can get 2. If we push this 2, it's 2 times 2, so it's 2 squared. If we push this 2 up, it'll be 2 cubed. Push this 2 up, we'll get 2 to the 4th. Push this 2 up, we'll get 2 to the 5th, etc., right? So basically the idea here is we want to know the power p such that n is approximately 2 to the p, right? And what I mean by approximately is that it fits between 2 to the p is less than n is less than, say, or I guess actually it's 2 to the p minus 1 is less than or equal to n is less than or equal to 2 to the p. That's the most technical answer of what we want. The good news is that we already have a mathematical function that everybody loves. Actually, for some reason, everybody hates this one, but what is that function, Ben?
Everyone loves its log. It's log. It's
Yeah,
big, it's
so
heavy, it's wood.
So you have to hit this with log on all the sides, so you get like p You'll get, I'll just call it LG of n is less than or equal to p, and is less than, or I guess I'm saying less than and not equal to p minus 1. So that's the point here, is that...
You know what, you guys, did you just see what DJE just did? He wrote log, but he didn't include the number at the bottom, which means, guys, means he dropped the base. Oh! I know, Eric. We're not friends anymore. Did you just leave the room?
So, as...
Anyway, sorry.
Oh, it hurts me. I mean, it's only as stupid as the joke. What is the integral of 1 over cabin d cabin? Of course, the answer is
log cabin.
Log cabin.
How was that clever and terrible at the same time? Yep.
So,
I was voted most likely to be clever and terrible.
But the point is that if you write LG, what that means is log with a base of 2, right? When you just write LOG, usually in most contexts that means a log base 10. Unfortunately, there are actually books and other contexts where this also means log base E, so it's actually a little dangerous, but most of the time, so I'd say 80% of the time, 80% of the time it's log base 10, and the other times you have to just read carefully. You always want to be careful about this one.
Ken gets...
That's just a little bit of helpful hint about log base 10. Anyway, and then ln is the log natural, right? So it's log base E, but no one cares about that, right? Because what does log base E do in computer science? I don't know of too many algorithms that actually run in like e to the n time.
It's a thing that comes up, but not often.
Not often.
Okay, here's my math-phobic explanation of log. So so it's very common to define log as the inverse of exponentiation. But if you are taking the log base 2 of a number, what you're asking is how many times can I integer divide that, more or less. Essentially what you're asking is how many times can I divide that number by 2 until I get to 1. That's what you're asking mathematically. And I know those of you who, like Eric probably, if you weren't yelling at his dog, Eric would be like, well, that's not precisely correct. And he would be right. But it is also an intuition that's kind of how, intuitively, yes, that is what it means. It's the amount of times that you divide a number by 2 to get 1. And that's what binary search does, is you take a list of size n, and in its worst case, it's going to divide that list in half a bunch of times. And so the question is, how many times? Well, we have a math device, a math function that you can give it n, and it will tell you how many times you can divide n by 2 to get 1, and that's log base 2. So that's why when you see division or halving, you should start thinking about your good friend, the log. The log is your friend. It's your buddy. It helps you describe these weird division things.
Yeah. The nice thing about log in computer science is that you might think like, oh man, there's all these complicated log rules. I don't remember all that. But here's the thing, like, we're not asking you to know any of that. All we're asking you to know is that when you divide a list in half, and then you do that again, and then you do that again, and then you do that again until you have a list of size 1 or 0, that's log. And the runtime is never going to be some, theres a whole family of interesting and horrible facts about the natural log or other logs, about how, like, the natural log of any integer n is transcendental. Uh,
Does
there's
that
some.
mean Bill Murray was in the movie about it? I don't.
What it means is that none of them are solutions of polynomial equation. I guess other than for not equal to 1. So none of them are solutions of polynomial equations. So not only are they not irrational, or not only are they irrational, right? They don't have a finite decimal expansion, but they also cannot be written as the solution of a polynomial equation.
You know what? You know what I'm kind of upset about right now?
I don't.
I actually think that's kind of an interesting fact.
No, it is definitely an interesting fact.
I'm kind of glad you taught that to me, and I'm a little mad about the fact that I'm glad you taught that.
Yeah, but no, we don't. This is number theory. We don't need this, right?
Oh, okay. So you're gonna So you're gonna look down your nose at it.
No, look, it's a great and beautiful fact,
Uh-huh.
and the fact that certain numbers are transcendental is just amazing. Like E is transcendental.
Are
Pi
there any transcontinental numbers?
I don't know.
Oh.
What would that even be? Okay, yes, you've confused me.
We've strayed.
Okay, let's do merge sort.
Yeah, let's do merge sort.
Let's do merge sort. So what does merge sort do, right? There's quick sort. We can talk about quick sort in a second.
I think we should just leave it at merge sort.
Maybe.
Quick sort's hard to talk about because it's like, I don't know, spooky.
Well, okay.
It's interesting to talk about. We'll see. Let's talk about merge sort though.
So there's two functions in a merge sort, right? There's the merge sort itself, which is this thing, right? We're not going to talk about this. Let's talk about this. We want to just talk about the merge function, right? So what does it do, right? And here's the great thing about it. We know that the first list and the second list are approximately the same size, maybe plus or minus 1, right? Because we're always dividing things in half. So plus or minus 1, first list and second list both have size. Let's call it k, right? All right, cool. So how long does this algorithm take? Well, what does it do? It loops through until every item in the first list and the second list are eaten up and sucked into the merge list, right?
Yum.
So how many steps does that take? Well, there's 2 lists of size k, so merge must take 2k operations approximately, right?
Yeah.
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 Yeah, nothing more. Like, you look at this loop here, and it says while the first index is less than the length of the first list, and this index is less than that. Well, and then this one will take this the rest of the way, and this one takes this the rest of the way. So if the lists are size k, then it takes literally 2k operations. So let's write that down. And merge is on 2 lists of size k, and we're just going to say that's O of k. It's okay.
Okay.
I just did a dad joke, just like Ben did, but mine was less awful because it was quick. It was quick and.
Yeah, you pulled that Band-Aid right off.
I know. I did it, and I do apologize. So anyway, let's look at.
I don't apologize for mine.
I know. That's the difference between us. So here's half list is length of list divided by 2. And then here's where we merge the things. Now, let's pretend like this isn't making all these copies. Though actually it doesn't really matter. Let's just pretend like it's not doing that just for the sake of simplicity. So it's going to merge sort half of the list, and then it merge sorts the other half of the list, and the other half of the list, and the other half of the list, right? So how many times does merge sort get called, right?
So you might be asking me, how many times am I dividing the list in half until I get to a list of size 1, right?
That is exactly what I'm asking you.
Wow. I wish we had some sort of mathematical object or thing that would help us with that answer. If someone, I wonder if anyone in chat has heard about a math thing that tells us how many times we can divide a number by 2. till we get 1.
Yeah.
Yeah.
That would be like, I'm going to invent such a thing.
Okay. No. Let's not do that. Let's not do that. That's
I scared you. Listen to the fear.
Like, oh no.
Listen to the fear.
It's log. Yes.
So
Brandon,
basically,
yes, it's log. So we're saying we're gonna do an algorithm that takes n time. We're gonna do that log many times. Ooh.
right? And so technically, this is not just O of n, it's O of k, where k ranges over all the crap. But guess what? We don't have to care about that. We can just overestimate, because O is an overestimate, and just say it's O of n. And so then this thing is going to be O of, traditionally we say n log n, like this. I think the general reason for this tradition is because it's nice to put the n in front, and then you don't need the parentheses. I think that's literally the reason why we call it n log n, and we don't call it like log n. That sounds horrible. Yeah, aesthetically, aesthetically that's awful. This is aesthetically pleasant.
Mm-hmm. Cool.
So basically what this means is it's not quite... Let's just talk about what this actually means, right? This is not as good.
Uh-oh. The stream got sad.
Oh, did it?
Oh, it's back. It's back.
Oh, I see it. As, say, a linear time thing, right?
No, it's not as good.
I like how I just called it a thing. What I mean is an algorithm, but whatever. So it's not as good as a linear time thing. So it is true that n is less than or equal to n log n. But it's also true that it is less than n squared. I mean, technically this is also not equal to, but I want to imply that it's way closer to this, right, than it is to this.
Much closer.
And you know what? Let's just graph them all and show that that's actually the case.
Let's graph it. Let's go to Des Moines.
Here's
back to
n.
Des Moines.
We are.
Des Moines.
And then here's n log. I'm just going to use natural log because we don't care.
Wow.
We know well, there is a simple fact.
E is pretty close to 2.
Yeah, well, there's an even better fact that says that all logs are the same up to a constant, right?
Oh, that's a good fact.
Yeah, the change of base formula tells you that basically any two logs are the same. So, let's increase the domain.
It's time to increase the domain.
Here we go. And so you see that it is true that n, this little line right here, is actually bigger than both n squared and n log n for a while, but here's where it intersects and it becomes smaller. And here's n squared, so n squared blasts itself up to infinity pretty nicely.
Yeah, somebody thunder punched it to the moon.
And so
whereas, like,
as we zoom out, we see that the behavior of n squared is starting to go like really vertical, right? And this thing is starting to look like x. But if we added another function, let's say y is equal to, say, 50x.
It's also,
50x.
This is a little skewed because your x and y are going at different scales.
Well, yeah, no. So, because this is exactly what I want to show. What I want to show is that here, right, here's x, here's 20x, right? Now 20x is big, but it's still just O of n, right? Or I guess n. So 20n is still the same thing as n, it's just 20 times that, so the constant is just 20. And we see that at least here, right, it looks like the blue thing, n log n, is just between here and here. So it looks... So that's what I'm saying, is that asymptotically, n log n looks way more like n than it does like n squared. But eventually, and let's see, how hard do we have to go out to get it to cost 20n? I think we might have to go out to... Oh god. It might be up to 10 to the 20th power or something like that. Almost there. Oh, there we go.
There we go.
There we go. So eventually it does cross.
And it looks like the x squared is just part of the y-axis now.
Right, yeah, so x squared, by the time you get off to 5 times 10 to the ninth, that's like, what, like 5 billion? You know, it's so high up that we can't even see it on this graph. We can still see x, we can still see 20x, and we can still see n log n, right? I keep flipping between n and x, but who cares? The point is, we can still see n, we can still see 20n, and we can still see n log n. So that means that they're kind of doing the similar thing, at least for inputs of size less than 5 times 10 to the 10th, which is 50 trillion, right? So if you have an input size that's larger than 50 trillion, you have a lot of input. So anyway, so that's kind of the argument here. Okay, should we say anything more about asymptotic analysis?
No. Well, no. I think we can just call this a
Why
day.
don't we talk about what we're going to, given all that we've said, why don't we discuss what we're going to expect on the exam about it?
Oh, okay.
So,
Well,
I think a fair question would be something like, if we give you, say, a function that is made up of for loops, you can tell us how, you know, what big O it is and stuff like that. So for instance, if we have like a 4, you know, and a 4 and a 4, you know, and this is some function, and all of these depend on the length of the list, etc., then you should be able to say that this is O of n cubed, right? That's, I think, you know, I think that's a reasonable thing to say, right? We won't ask you.
recursion.
We won't ask, so no recursion. Because even though it's important, it's also more of a 341 thing, and it's... So...
We haven't really discussed the fact that consecutive for loops are additive, not multiplicative, and what impact that has. So maybe we can put that on the exam.
Maybe, yeah. Well, yeah. So I mean, if you have a for loop, and then you have another for loop like this is what Ben's saying, which is, I'm sure it was clear to you, but I'm gonna say it again in different words because I'm gonna pretend it wasn't clear. But these are not nested, right? So this for loop and this for loop are not inside of each other. Then this is still O of n, because this takes n steps to run, this takes n steps to run, but this for loop doesn't run this for loop, right? So it's not saying each time you go into this one, run this one n times. It's saying, do me first, I go n times, and then do the next one n times. But that's just, it's really just like 2n operations, which is just O of n. So I think that's a reasonable question. I think maybe we should... I think it's reasonable to ask, like, is n like O of n squared kind of questions. Those are pretty simple. And the answer is always, is this function less than or equal to constant times this, right? Like, that's really what we're looking for. We're not going to give you... The list of functions that we're going to basically stick to is like n squared, n cubed, maybe the square root of n, which you should know is less, but like, maybe.
No square root of n. We don't... What? Nah.
Okay. Log of n, and log of n. So this is like as much recursion as you have to know. Is like the sorts that run in n log n time, and then basically you just have to know that n is less than or equal to n log n is less than n squared, right? It fits somewhere. It's slightly super linear, but it's not quadratic, and that's all I expect people know about that. And then of course, so actually let's just do this on a separate slide so that I can actually do this. So we have log. Oh no, we don't have log. We have constants, right? Which are less than logs, which are less than n, which are less than n log n, which is less than, say, n squared and n cubed, which is less than, say, 2 to the n. That's really it. Anything else that you want to include on this list?
I don't know. I'm looking at the study guide I wrote to see. So here's what I have for the previous final exam study guide. Define big O and big omega in terms of best and worst case performance. Define big theta in terms of big O and big omega. Rank the following functions from slowest growing to fastest growing, constant, log, n log n, and quadratic. Analyze the best and worst case performance of the following functions: bubble, select, quick, linear, and binary search. Provide inputs for the best and worst case scenarios for the above algorithms. We might remove that. You want to remove that one from the study guide?
Given how it went last semester, yeah.
Okay, it's gone. See? The benevolence of Professor Hamilton knows no bounds. And define log in terms of division.
Yeah, that's a pretty good one.
Okay. So
I mean, and maybe what we'll do is we'll have you argue, right? That binary search takes log n steps, right? And you have the argument that we gave in class, and also there's the internet. So basically what I'm saying is review this argument, right? Review the argument that, whoa, I just deleted everything. That binary search takes log of n steps, and that's a good argument. Things like that. I want to restrict. So I know that I'm speaking about this. This is kind of an internal conversation between Ben and I, but I'm definitely thinking that we will restrict the amount of big O stuff that makes it onto the final exam.
Yeah, it's not going to be a large amount.
So I will probably release a more consistent or complete document on exactly what I intend to put on as a big O, big omega, big theta question, so that there is not what happened last semester should not happen again. Is all I'm saying. And
I just popped into chat the final exam study guide, which I just looked over, and it appears to be accurate.
Okay, so yeah, I mean, we'll take a look at it, and yeah, we're just gonna make sure that the questions are narrow in scope, so that you guys know exactly what to expect. Because, yeah.
Since we're getting this, do we want to discuss now?
I mean,
we're doing another take home.
Yeah, I mean, we hadn't finalized. I think we sort of said the final exam is going to be like exam 2, right? Yep.
Yeah.
I think that was literally all we said to each other. So presumably, what I'm going to do is I'll release it on the final exam day, and you'll have some number of time units to work on it.
Which is the Friday after this Friday.
Yeah, and I'll maybe we'll give you a week.
Monday or a week?
Or I don't know. Fine.
I think finals end on Wednesday.
Okay, then we'll give them until that Wednesday.
So you'll have from. It sounds like we're saying you'll get the final on Friday, and then it will be due by the last day of finals, which is Wednesday.
I think that's what we'll do.
That's our work in progress. We reserve the right to revise that schedule.
So I know. So here's the one thing, and I know that all of you loyalists here would never mutiny against good old Captain Eric Bly, but point is, when the exam was posted, it got put up on the internet and answered very quickly. And so the problem with that is if I give you a long time to work on the problems, then unfortunately I risk that again. If I give you like 2 hours to do the problems, then the risk is that, like, if your computer crashes, if whatever Blackboard does to us, if we only have 2 hours, then we're going to be giving extensions to a ton of people because everybody's going to be not finishing on time, is my assumption, right? So
don't put the thing, tell everybody that you know to not put the stuff up on like Chegg or Course Hero or any of these other places.
Because that's actually the primary factor in me not giving you guys a lot of time. Is if I feel like it's going to get posted again, That would be the one thing that would.
Well, the other factor is we want to get all the grades done reasonably as well.
Well,
Is another factor.
so
the grading is another thing.
well, I don't care about that because we have so much other things to grade that if we're not grading the final exam, then we will be grading projects. And then as soon as the final exam comes in, then we'll grade that. So, like, there is so much grading to be done that it doesn't matter if we give them a few extra days on that. That does not affect my decision in any sense. Because if I don't have the final by Friday or Monday, that just means the TAs have 2 more days to grade other things. So that's completely, I don't know. I don't care about that. But the cheating thing. Oh, that killed me, man.
It's gone up this semester, guys.
I almost had a little emotional.
You almost had emotions?
I really did. I had some emotions when, after spending 10 hours tuning the questions, deleting questions, rewriting them over and over and over until I tuned that exam to a point where it was doable, but not impossible, and it was hard in the way that it should be hard, and within 3 hours it was all solved on Chegg. I will say I was really unhappy.
You felt a certain kind of way.
I was ready to just take the exam down and be like, it is canceled. Like, so, but you can't do that, so, but I definitely felt like giving up for a few days. So, if it appears on Chegg, and we have the same kind of thing again, oh god, let's just hope that doesn't happen, because the punishment will have to be at least as bad as the punishment is for me, which is, I don't know.
Anyway.
Yeah.
So we're over time. You guys are free to go at this point. So.
Oh yeah, I mean, class has been over for 5 minutes.
Class has been over for a while.
There
will be more official announcements near the end of the week about final exam timing and things like that. The point is, there is a final exam study guide up that I've posted here. It's in my slides, which are linked in the course website. And it's been available since the first day of class. The only thing I changed just now to take something off of it at Lord Eric the Great's benevolent command.
Oh, Lord. Yeah, no, I definitely feel more like Captain Bligh.
DJE.
Yeah.
So yeah, but anyway, we know none of you guys. We're not really worried about the people in the chat right now. But if you're watching this video and it's a thing to be mindful of. Anyway, anything else we want to say before we sign off? Next class is going to be fun. Let's tune up the mood before we go. Next class is going to be so much fun. So this whole semester, we've been talking about forbidden magics, and you can't use that, can't use that. And the reason we do that, we don't do that because we're mean. We are mean, but we don't do that because we're mean. We do it because this is a comp sci class, and we want you to learn how to build tools from nothing. To cobble together from just your brain and your logic and all your good muscles, how to make anything there is out there that is computer software. But that being said, a lot of you well know that there's a lot of libraries and powerful tools out there. So next class, on Wednesday, we're going to talk about what tools are available out there and what are just some fun things you can do now. You guys, you go from nothing to having a lot of skills in Python and understanding a lot of things. This is a pretty aggressively paced class. We always get that feedback, and we know, but we're trying to prepare. And you have a lot of skills now. So next class, we're going to talk about all the really neat things you can do with your knowledge of Python that you have thus far. So we're going to talk about robotics, web development, artificial intelligence, all that good stuff. And also just kind of get you excited about being a comp sci major, or maybe if you're not a comp sci major, being excited that you now have, programming as a tool in your utility belt of awesomeness.
Yep.
So get pumped. And yeah, don't cheat, guys. We take academic integrity very seriously. Both of us have degrees from this school, so we take it very seriously. And it unfortunately takes a lot of our time that we don't want to spend any time on it, but we have to uphold the quality of the degree, and we want to protect, make sure all the you guys that are doing all that hard work are
Yeah, I
putting
mean,
in
really, I
good
guess
work.
that's the best and most charitable way to say it, is that we're punishing them so that we can protect the value of your degree.
Yeah, and also just the value. I mean, that's the thing that makes me the most upset with this Chegg stuff and things like that. Is I know all you guys, you're on Discord, really working really hard on these projects, and you're
And
growing and
I
you're
do
getting better
like,
at this stuff.
I will like, I
And
say I do like seeing discussion about, things about the project on Discord, because with that on our Discord, because it keeps everything safe. It means that, like, if you guys start straying, I can be like, okay, that's enough about that. But, like, as long as I don't step in and explicitly tell you guys, like, hey, you're crossing the line, and even if I do, that I'd rather say that than have to catch cheating on the project in the end. So I
yeah,
encourage discussion. I want you guys to have camaraderie with each other and talk to each other, especially in this era of everybody living in their own houses, right?
yeah,
So I
yeah.
want,
So
I really do want
we don't like
this.
to deal. We've spent about, I'd say, 30 hours over the past 2 weeks on academic integrity violations and stuff like that. We hate every second of it. We want to spend time
Oh yeah,
figuring out ways of like teaching you guys better and making the class easier and running it more smoothly, but we also have to protect the hard work that all the honest students put in, which is almost all of them. But anyway, yeah, next class, get hype. We're going to learn about web development. I'm going to show you some videos with robots and like things you can you can bling out your video game battle stations with. So 30 hours, I'd say that's about right,
30
especially
hours
between the
of
two of
30
us
hours of what? I
doing
wasn't
academic
paying
integrity
attention.
stuff for the past
Oh,
2 weeks.
ah. I have no idea. It could have been. I mean, it was basically an entire week consumed just doing
In
that.
the
So,
yeah, the meetings alone were probably about, well, we did 6 hours, no, 7 hours for both of us. So that's 14 just for the meetings, and then we have to go through, and we want to make sure that we're not we're accurately catching things. So it's a lot of time.
oh yeah. I mean, so anyway,
But anyway,
but
on
yeah.
to
So
nicer
so we're
topics.
gonna, and we might also do some Flask, and if we don't have time for that during Ben's lecture, maybe Ben and I will get together and do a special non cs201 lecture. It's just like an addendum material, which we were supposed to cover it today, but as with everything, we only cover about half of the stuff during an online lecture that I'm supposed to cover. I'm so slow in online. I don't know why I'm so much slower. You realize this, right, Ben? Like, I'm slow. Are you slow?
Uh, yeah, I'm slow. We're slow for different reasons. No, we're slow for the same reason. We both get distracted. You get distracted by mathematical precision, and I get distracted by just like shiny objects or noises.
Yeah, I mean that's a decent assessment. Well, and I admit that I took some detours, but this is Big O, right? Like normally I don't get so caught up
This is
on.
your jam, though. This
Well,
is
I
your
mean,
jam. DJE. This is DJE's jam.
I mean, yeah,
Yeah,
every you have to understand the nature of a mathematician is that, like, all things should be converted into mathematics and then made fun of.
yeah.
So,
All this mathematical stuff, guys. It's all in service of his night his night job of laying down the beats.
yeah,
It's a mathematic, man. You got your time signatures and your harmonies.
yeah, time signatures are kind of cool because, in a sense, there's a little bit of like projective geometry going on with them.
Yeah, yeah,
Because like a
yeah.
4 time signature would be the same thing as an 8 time signature, really.
But I mean, I've said this in your 203 lectures, but most of the time I see you outside of the UMBC campus.
Yeah,
You've got like just the biggest headphones on,
that's true.
and well, see, I mean, you're a pioneer. So a lot of people, if you've seen DJs where they're holding one of the cups up against their ear and not the other, like
No,
because the
I
left
definitely
ear,
hold both
it
cups.
sounds
Pretty.
Well, so Eric started that years ago. That was his thing, and other DJs started copying that. And then once they started copying that, he realized, he started something he wasn't proud of, and he wanted to get more back into the tuned sound in the headphones. So you go back to actually fully wearing the headphone now, right?
Yeah, I definitely had a lo-fi period, and then I'm back to, I guess, regular fi.
Yeah, you're back to regular fi.
Yeah.
But you keep the beats thumping, and
Oh,
that's what I respect about you,
Jesus.
among many things.
Yeah, that is definitely what you respect about me, is that some kind of beats are thumping. Man.
The other thing I like how authentic you are in your gigs. I've never seen you at it's always a pop-up club. You're never
Oh,
at like an established place. You're always at some unmarked, it's usually a preschool, but then like one night every 3 years
yeah, I can't do
it
anything too
becomes a pop-up.
mainstream. It hurt my cred.
Yeah, yeah. And that's your cred is gold. You think Bitcoin is valuable? DJE's cred is the happeningest fiat ever, right?
I suppose.
So I love that we bookended this lecture with grotto and happeningest fiat, and I think we need to leave this dough to prove for a while and just call it a day here.
I would agree.
Yeah. Okay.
That's
good.
that's the first thing you said I've agreed with.
Ever.
Yes, ever. Literally in history.
Yeah. I'm pretty disagreeable. People say that about me. They're like that.
Well,
that's
you like to take contrary positions.
Oh, I love it so much.
You like to argue
I argue
a
for the
case.
sake of arguing.
Yeah, and I definitely know that by now.
Yeah, I know. I'm pretty agreeable in lecture, but people don't know that about me. That like, if you come to my office, I'll debate anything. I'm surly.
Whereas I don't know, like I guess I'm argumentative, but not for the sake of being argumentative. I'm just strong my opinions. Your opinions you don't hold nearly as strongly, but you're
I'm very relativist.
But you are definitely, as soon as I state something, I think it's something in your psychology dislikes the way I declare things with certain levels of certainty. And when I do that, you react against it, and I totally understand. It's like, he's too certain about this. Gotta fight him. And
yeah, I am pretty allergic to organization and certainty.
Yeah, and
schedules. Ugh.
Yeah, you see, it's
that's why I chose linguistics. You chose math, and I chose linguistics. Linguistics is the ultimate field of but that's also just never always true either. Linguistics, it's the discipline of like, there's rules, but not really. You can learn them if you want.
Oh, there's worse fields in terms of that, but we won't get into that.
All right. Yeah, professors really just said the equivalent of I'm a head out. So we should say
I'm out. Peace. We out.
Oh, whoa! Don't get too DJ. You got to make these kids come find you when you're doing a gig. Don't give them too much.
Outro scene.
The special sauce. Now.
Yeah.
They gotta come scope out your happenings.
Yeah.
Yeah. All right. Let's just end it. Let's not even do the darkness. It's over.
And the darkness is going on right now.
No, we should just end it.
I'm gonna do it. I'm doing it.
Out.
It's
Goodbye.
over. Goodbye, everyone. Over and out.